In this section, we are going to be describing the process for coming up with the derivatives of compositions of functions. So, as general as possible, something along the lines of f of g of x. An example of one such composition of functions would be y is equal to x squared plus 1 raised to the third power. In this case, we'd be saying that our outer function, f of x, would be the cubing function, and our inside function would be x squared plus 1. Now, if I asked you to differentiate either of these functions, I feel like you could probably do so fairly easily. It should be pointed out, though, that if we used a little bit of algebra, we could also expand this thing completely. This would be x to the sixth power plus 3 times x to the fourth power plus 3 times x to the second power plus 1. That's if I were to write this out as x squared plus 1 times x squared plus 1 and times x squared plus 1 and expand the whole thing. Written in this form, however, the derivative is going to be a piece of cake. Use of the power rule a couple times here. This will be 6 times x to the fifth power plus constant multiple and power rules will be used. And once again, constant multiple and power rules. The constant term goes to 0. So we can simplify this to be 6x raised to the fifth power plus 12x raised to the third power plus 6x. And just because it's a cool thing to do, this actually factors really nicely. If we factor out a common factor first of 6x, the remaining part would be x to the fourth plus 2x squared plus 1. Now what remains after factoring out the greatest common factor actually factors itself really nicely as well. That's x squared plus 1, quantity squared. So how does this derivative relate back to talking about these things as compositions of functions? The reason I bring this up is because when it was raised to the third power, it was fairly reasonable. But what if I asked you to do this same technique with x squared plus 1 raised to the 117th power? Does that seem as reasonable? I'm hoping probably not. So it's because of functions like this that we are going to investigate what is known as the chain rule. So the chain rule states the following. Let y be some function of u, and let u be some function of x. Now this is where u is going to be some expression and not necessarily just a variable. So u is an expression. In terms of a composition of functions, f would be known as the inside function, f would be known as the outside function, and g would be known as the inside function. So you'll notice that if we actually performed that substitution, we would have the composition that we talked about just a moment ago. The chain rule states the following. If I'm interested in finding the rate of change of y with respect to x, I would be taking the rate of change of y with respect to u and multiplying by the rate of change of u with respect to x. The mentality to get into here is that it's as though the du's are canceling each other out. What we're saying in terms of Newton notation, though, is that this would be f prime of u, but u is g of x, multiplied by g prime of x. Getting into this mentality is known as the outside-in version of the chain rule. This is known as the this one's inside out, and this one is outside in. We'll discuss both as we proceed in future videos.